The concern of the element distinctness problem is to figure out whether a list of elements contains two instances of the same element. In other words, are all elements in the list unique? There are two possible answers. Yes, all are unique, and no, some are the same. So, given an input x, if there are no repeated elements, the answer is yes. If at least a single element repeats itself, the answer is no. We are using the comparison-based model, so we can only compare two elements at a time, which means that when we develop an algorithm, we cannot apply hashing using which problem could be solved in O(n) time by simply checking if our newly seen value is already present in the hash table. If present, answer no. If got to the end without seeing anything repeat, answer yes. Here's the hash table Python algorithm solution. You can see that the loop runs once, and elements 1 and 9 are detected to be present in the set more than once. Another way to solve this is first to sort our list and then go through each consecutive pair and compare them. If they are the same, answer no. But if we got to the end, answer yes, all elements are distinct. Here's the algorithm for Python solution. We claim that it takes at least O(n) log n time to solve this problem, and even though the analogy with sorting is solid, we need to prove this time for this specific problem. We want to get to something that resembles the argument for sorting lower bound, essentially prove that there are n factorial possible solutions. Then, like in sorting, decision trees, because we are sticking to comparisons to get to the solution, we can imagine the problem as nodes in the decision tree. With each comparison, we go deeper, and if we are lucky with our picked list, or unlucky, depends on what we apply this problem to, and all elements are in fact distinct, we arrive at the leaf that says yes, indicating that all the elements in the list are distinct. Otherwise, we arrive at no if on the way we detect that any two elements are not distinct. To understand this problem even better, we can imagine our list as a point in the n-dimensional space. So for example, an input list of x equals 2, 3 in 2 dimensions will be a point on a 2D plane, so something like this on the screen. Now notice that if our list is 1, 1 or 2, 2, it lies along this diagonal right here on our 2-dimensional plane. Essentially, you can think of this diagonal as the instances of the list for which the answer is no, where not all elements are distinct. So we went from checking if all elements are distinct to checking if our list, when considered a point in space, happens to lie along this diagonal. The same argument can be made for any n, meaning an input list of any size, because we are still looking if there is an overlap. With 3 dimensions, we get something like this. If x1 and x3 are the same, let's put these points down or on our diagonals. So it's going to be here and here. You can see that they are actually same anywhere on this plane. Anywhere on this plane, x1 and x3 will be the same, even when x2 is changing. So it's independent of height in this case. You can think about it this way. And similarly for x2 and x3 being the same, there is a similar plane. And of course for x1 and x2 being the same. So for x2, x3 it would be somewhere here. And for x1 and x2 it would be this and this right here. Same logic applies to higher dimension, except it's quite difficult to visualize them, so we'll stick to 3 for further proofs. Now, with this out of the way, we will make some claims which, when proven, state that there is in fact n factorial possible solutions. That is what we want to prove. Remember to keep both the tree-like representations and the point-in-space representations in your head for the proof. So, claim number 1 formally is, let region L be the instances for which the leaf L is reached upon execution. We claim that that region RL is connected. Geometrically, a region is connected if taking any 2 points in that region, they can be connected without going outside of that region. It's easier to work with convexity, where a convex shape is just a shape that can be connected with a straight line. So we will stick to convexity, it's just easier to use. For instance, a circle is convex, but a cashew-like shape is not, because a straight line might go outside of the shape in order to connect two lines. Informally, this claim states that given an input, the exact values of element are not important, only how they compare to each other. So as long as they compare to each other in some way, for instance, x4 is always smaller than x5, to make this a little bit clear, consider the following. We have two lists, 3, 4, 8, 3, 5, 8. Elements that are at x2, though different in value, compare to the other elements in the same way. So going through a decision tree, we would arrive at the same leaf. That is, when asked if x2 is bigger than x1, and if x2 is smaller than x3, we take the same path along the nodes of the tree for both lists. That's what we mean when described informally by region being connected. Now let's go back to the point in space representation. I will use this visual simulation to prove the previous claim that as long as x1, x2, and x3 compare to each other the same way, they are in a connected region. In the simulation, we can see the planes along which the values of x1, x2, and x3 are the same, similar to what we drew before. And they're best viewed from this angle. Between them, there are regions that we are talking about, and the colored spheres represent the permutation of x1, x2, and x3, so we can change their values right here. I will move x2, and you can see that as long as x2 compares the same way to x1 and x3, each sphere on the permutation instance stays in its connected region. So here I'm moving x2, and you can see that the blue sphere, for example, stays in its connected region, and every sphere stays in its connected region. I can also move x1 and x3 with respect to those. Claim number 2, formally, let x be x1 through xn consist of distinct elements, and let y be y1 through yn be a non-trivial permutation of x. Then x and y must reach distinct yes leaves. Non-trivial permutation of x just means that y is not the exact copy of x, so at least two elements have swapped places when we went from x to y. And reaching distinct yes leaves means that each permutation of x lies in its own region. I will again use the simulation to prove that this claim is true. Look, as long as x1, x2, and x3 compare in the same way, they stay in their region. And as soon as they compare to each other differently, they cross their region bounds. They basically swap regions. If we change their orders enough, we can get, for example, the blue sphere into each of the regions. In two-dimensional space, there would be just two regions. In three-dimensional space, there is 3 factorial regions, so 6. And so for each n-dimensional space, the number of possible permutations is n factorial. So our second claim is proven. X and y, being permutations of each other, will reach distinct leaves in the decision tree. And by distinct leaves means that each of them gets their own region. Again, only when they are swapped is when they actually switch regions. And this way we can get, again, for instance, the blue sphere into completely any region that we want. So by considering the two claims, we can see that there are in fact n factorial solutions, and with each comparison of two elements we're reducing the possible solutions by half, which means that it will take at least n log n comparisons to get to our solution of yes or no in the worst case. This is the end of the video, and I had quite some fun studying this problem and getting to visually prove it in the easiest way possible, and I will greatly appreciate constructive criticism. Thanks for watching.